All right, let's do a little lecture on torque just in case you missed it or if you're falling asleep. Anyways, we have this thing called torque, and I usually do it with the squiggly T. That's a tau, Greek letter. And so torque is going to be represented by the Greek letter taus. Don't get it confused with T. Sometimes we might use tension. Tension's going to have like a straight across on the top. Torque's going to have more of a squiggly tilde. And a torque is sort of like force, whereas force is going to cause some kind of acceleration based upon the mass that you're applying it to if you have an unbalanced force. A torque is going to do something like that. It's going to cause an acceleration, but it's going to cause an angular acceleration. And so an angular acceleration is going to change the number of radians that we travel through per second. Radians is, basically the angle of measure that we would be talking about if something's going to be rotating. So an unbalanced torque is going to cause some kind of acceleration, but it really also depends upon the mass of the object, and it's really dependent upon where that mass is placed. Now, we would have talked about inertia a little bit in class, hopefully, by the time you're looking at this video. So torque is equal to a force applied at some radius or some distance away from a center of rotation, and you got to make sure that that force is perpendicular to that distance. And we'll talk more about that when we get to this example. Torque is also equal to inertia times alpha. And so inertia deals with the mass of the object. It deals with where the mass is placed with reference to the axis that that object is spinning. For instance, this object here, we have a flat bar that's going across. Think of it like a seesaw at the park. I'll draw some grass here so it looks like a park. But the seesaw is going to resist a change in motion. And so the more mass it has, the more force it's going to take to actually turn this thing or actually rotate this thing, if we were to do this. But it also really depends upon where the force is applied. Because if I apply the force right in the middle, then there's no reason for the seesaw to rotate. Like, think about the door. If you're going to try to open the door, you're going to pull on the handle, and really you're pulling perpendicular to the distance you are away from the hinge. Okay? If you were to push like in where the hinges are, you're not going to open the door. If you're pushing really close to the hinge or pulling really close to the hinge, it's going to be really hard to open or close that door. So force definitely matters, but it's also the distance away that you are applying that. And so if you have an unbalanced torque, just like how you have an unbalanced force, you're going to have some kind of acceleration. And it's going to depend upon the mass, or in this case, the inertia of the object. So looking at this system, we're not going to worry about the acceleration just yet. We're just going to talk about torques. So we have this seesaw, and let's call this side, what do you want to call it? Maybe like 3 meters? It's actually pretty decent. If this side's 3 meters, that side's 3 meters as well. For the full length here is 3 meters. So we have a total of 6 meters across, and we're going to have a little kid. And this little kid's going to sit here and give him something to hold on to. All right, so this little kid is sitting here and he is sleepy, sort of happy, but he's sitting there and he is applying a force because of gravity. Gravity's pulling him down. He's applying a force straight down at the edge of this seesaw. Now, what's going to happen if we just let time play out? Well, obviously it's going to do this. Okay, it's going to be unbalanced, and this is going to go down until it hits the floor right here. And if it hits the floor, then the floor would be pointing a upwards force or a normal force on him to balance it out, and he just stays there. And so the system would be at equilibrium at that point. But really, he has a friend, and we have this friend that's going to sit over here. But his friend is an older friend, it's a bigger friend, and we got to figure out where to place that bigger friend to balance the seesaw out so they can just stay here like this. Now, if we place the friend as far out as the little kid, let's say at the 3 meter mark, then you've seen this at the park before, hopefully, where you have a big kid, little kid, the big kid just sits down and the whole thing just goes dunk. And maybe the big kid really plops down, and that gives a whole lot of force, for that whole lot of change momentum right there, and just really catapults this kid up. And we don't want that. We want to keep our kid just nice and happy right over there. We're getting paid for some babysitting. We don't want the kid to complain. So let's say this little kid is a oh, let's say he's a 20 kilogram kid, maybe like around 40, 50 pounds. And that is applying a force downward. So right here, there's a force being applied straight down, which is going to be about 200 newtons if we use 10 for the acceleration due to gravity. So 200 newtons downward force right there, and it's a distance of 3 meters away. So, as far as torque goes, this kid is applying a torque to this system where this is going to be the center of rotation right here. Okay, and I look at the distance. I am 3 meters away. I'm applying a 200 newton force. That's perpendicular to that distance. So our torque on the right side going clockwise is going to give a total of 600 newtons, or 600 newton meters rather. Okay, so that's on the right side. So on the left side, we got to balance that out. And so if we have 600 newton meters of torque on the right side, we got to have 600 newton meters of torque on the left side going the other way. So wherever this kid is placed, say this kid's a bigger kid, we're not exactly sure where this guy's going to be placed. What we do know is that he's about, let's say, 60 kilograms. Okay, so he's going to be applying a downward force of gravity. His mg is going to be 600 newtons. Okay? And so, some of you have already figured this out if you're watching and paying attention. We got 600 Newton meters on the right side. We already have 600 newtons on the left side, so really, where should this kid be? Should probably be right here, sitting at the 1 meter mark. Okay? And why is that? And so if we look and we try to figure it out, and this is just using some intuition, a little bit of logic here, but the sum of all torque for this system, we want it to be 0. We don't want this system to rotate. We don't want to have any of this. Okay? And so you can call clockwise or counterclockwise positive. It really doesn't matter. Convention says that counterclockwise is positive because if you think about the unit circle, clockwise is going increasing in radians. That's how they kind of do it. But, it really doesn't matter. We did this one first, so let's talk about this one first. Let's talk about this kid. He's putting down a force, the F, of 200 newtons, and it's at a distance of 3 meters away. Okay, that's going to cause a clockwise torque. We got to counter that with a counterclockwise torque in the other direction. So we need to look at the force. The force that is being applied here is 600 newtons, and it's being applied a distance of r away from our center of rotation. Well, if we need this to equal 0, then r better be 1. Okay, and that's what we have. So it's a balancing act. Literally, it's a balancing act. Torque is going to cause an angular acceleration based upon the inertia of the object. And if you have an unbalanced torque, then you get that acceleration. Now notice we didn't care about the torque provided by the mass of the seesaw on this side and the mass of the seesaw on this side because it's symmetrical. Don't have to worry about that. But if we wanted to, we can say, hey, the mass of the seesaw on the right side is going down like that, and the mass of the seesaw on the left side is providing a force downward like that, and those two would be providing torque. And it's the same amount of torque, so really we just canceled it out. You didn't even think about it. You just naturally knew to do that. Okay? So let's move on to another example of torque. So say we have a wheel. And this wheel, imagine like a motorcycle wheel, back tire, or maybe your bike back tire. And it's got the outside of radius 2, and it's got the inside of radius 1. This is where the chain would be attached. I'm not going to draw the chain. But, this chain would be applying a force right here. It's going to try to pull this thing forwards. And so it would apply a force of tension. Okay? Now, the chain wraps around and actually goes the other way, and it kind of hangs down a little bit. It would actually be applying a force of tension here too. But hopefully, this tension is called tension 1. Hopefully tension 1 is greater than tension 2, because we want this wheel to be able to accelerate and actually rotate and keep on going and roll counterclockwise, or not counterclockwise, but clockwise. Okay, in the act of providing a torque here that's greater than the torque that's counterclockwise, this whole thing's going to start to rotate. And we can talk about different things. So let's say that this inside radius, let's call R1. Let's call that about, things about like this, maybe about 10 centimeters. Okay, and that's going to be 0.1 meters. And if you ever worked with like a, some odd speed bike, you can change the speeds, and you're going to change where that gear is which gear is being used, which chain, or what the chain is actually being attached to. Notice that if you want to go really, 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 really fast, you go to one of the smaller ones. If you want to go a lot slower, but make it a lot easier, you go to one of the bigger ones. Okay, it all has to do with torque. So the inner radius is R1, that's going to be 0.1 meters. The outer radius is R2. Let's see, make it about 60 centimeters. Okay, not sure what size bike this is, but let's just make it 60 centimeters or 0.6 meters. And we need to talk about the mass. What's the mass of this tire? Maybe the mass of this tire, let's say it's 1.5 kilograms. So the mass of this whole thing is 1.5 kilograms. Let's actually make this really simple. We've got this outside, and it's going to be a ring. Let's just call it a ring. And the inertia for a ring, the I for a ring, is going to be mr squared. And so the m, let's just call the m for the outside tire, let's say it's like 1.5 kilograms. Okay, we're going to plug that in, 1.5 kilograms. And the radius of R2 is going to be 0.6 meters. So 0.6 meters, and that's going to be squared. So if I get my calculator, take 0.6, and I square it, and I multiply that by 1.5, then I get about 0.54. 0.54, and look at the units, it's got kilograms and meters squared. So that's my inertia of the outside ring. Well, that's not the only thing that's going to be spinning. We got to spin these gears in here too. And let's call these gears a disc. Okay? And let's make those gears maybe 1 kilogram. It's a 1 kilogram disc. So the M inside of there is going to run out of room, but you just heard me say it, so it's 1 kilogram. And so the inertia of that inner disc is going to be 1/2 mr squared. Now we got to be careful which m and which r we're talking about. We're talking about the mass of this disc. So we have 1/2, the mass of the disc we just said was 1 kilogram, and the radius of that disc is r1. That's going to be 0.1 meters, 0.1 meters, and we're going to square that. And so I take 0.1, I'm going to square it, I'm going to divide it by 2, and I get about 0.005. So it's 0.005, or 5 times 10 to the negative 3. And that's going to be in kilograms meters squared. So, before we even start, we can find the inertia of the whole thing because we know the shape of the thing, we know what the mass is, and we're calling the outside just a ring, we're calling the inside a disc. You can simplify things like that. It's a lot easier to do that. So the total inertia here is equal to the inertia of the ring, 0.54, plus the inertia of the disc, 0.005. And so the inertia total is 0.545 kilogram meters squared. Now, you don't think that made a very big difference, and it really doesn't, but, we're just being complete about it. So if we apply a tension, let's say we apply this tension over here, and T1, let's just throw out a number, let's say it's like 400 newtons. Okay. T2, it's going to have a little bit of resistance on that. Let's just say it's just 100 newtons. Okay? And so if we look at T1 and T2, they're at the same distance. They're at R1. And so really, right now, if we're just spinning this wheel in the air, don't need to worry about friction or anything else like that, then the sum of all torque on this wheel is equal to T1, which is at the radius R1, okay, force times perpendicular distance, minus T2 times radius R1 again, because look at that, it's right there. It's 90 degrees. And we plug it in. T1 was 400. R1 is 0.1. Okay, minus T2, which is 100. R2, or R1 rather, is 0.1. And this is equal to, if you multiply by 0.1, you're going to move the decimal over once. If you multiply by 10, you're going to move it over the other way. So we have 40 minus 10, which is going to give you a total of 30. So 30 30 what? We're going to have 30, tension is in newtons, radius is in meters. We have 30 newton meters. But it's not energy. It's actually not energy. Okay. This is an unbalanced torque. So our net torque here is equal to 30 newton meters, which is also equal to I alpha. What is I? I is going to be our I total, 0.545, and that's going to be alpha. Okay? So if we take 30 divided by 0.545, that's going to give me an alpha. 30 divided by 0.545 gives me an alpha of 55. Holy cow. 0.05. And alpha is in radians per second squared. Now, is that significant? I'm not too sure. You know, what does 55.05 radians per second squared mean? Well, that's where kinematics comes into play. Let's say we allow this thing to accelerate for a time of 5 seconds. Okay, and we want to figure out the velocity of the edge after this 5 seconds is up. The initial velocity of the edge is going to be 0. Now, simple problem. Well, to find the velocity of the edge, we're going to take the initial velocity edge, which is 0, and plug it into our first kinematic equation, but for rotation. And we're going to say its velocity plus acceleration, alpha, 55.05. Alpha times r is going to give me acceleration of the edge. Now, what's the r? R is R2. R2 was 0.6. And we have a time of 5 seconds. So let's see how fast this thing gets going. 55.05 times 0.6 times 5 gives me, wow. This is a bike. 165.2 meters per second. Wow. Okay. Little excessive, I think. Just a little bit. But that's okay. We had a really light tire. For a motorcycle tire, the mass would have been much greater. But hey, we got some really strong legs apparently. So there you go. A little bit of torque. Unbalanced torque gives you an acceleration, an angular acceleration based upon the inertia. Remember, you have a table of inertias. But the most basic one is for a point mass. And this one is just mr squared. And a point mass is just, if you can consider the object you're talking about to be pretty dang small compared to the system, then it's pretty much a point. You know, think about, like, here we have the sun, which by the way is a star. And maybe way out here we have the Earth. And, you know, that's not even to scale in that regard. But something that's super small in the scheme of the system could be considered a point mass. But really, like, compared to us, the Earth is huge, so we would be point masses compared to the Earth. Or if you wanted to talk about your cells or your fingernail, that's pretty small compared to you, and so on. So if you can treat it like a point mass, there's your moment of inertia. If you can't, if it's actually of appreciable size, then hey, look it up in the table. So there you go. In case you missed it, there's some torque.